Okay, so what if I told you we could power, well, everything, for centuries, using fuel that we've mostly just been treating as waste? Sounds pretty wild, right? Well, today on The Explainer, that's exactly what we're digging into. We're looking at the source material behind a technology that could do just that: advanced nuclear reactors. Let's be honest, our digital world is insanely hungry, and its appetite for electricity, it's just growing at this unbelievable rate. I mean, think about it. Every time you use an AI, stream a video, or check your phone, you're adding to this massive demand. And all that demand, as our sources show, is really starting to push our current energy grid to its absolute limit. So that leads to the big question, right? How do we power all this stuff cleanly and reliably, like 24/7? It's a real puzzle. Look, solar and wind are absolutely essential, but they can't do it all on their own. And that's why this search for a solution is leading a bunch of innovators to look back, way back actually, to an idea from the middle of the last century, but completely reimagined for today.
Okay, first up, let's really get into this challenge of powering our digital world. Because as you can see, this is shaping up to be the biggest energy test of the whole AI era.
You know, when you look at the sources, you see this perfect storm brewing. First, you've got AI and data centers just exploding in their power needs. Then, we're trying to electrify everything, our cars, our industries, and at the exact same time, we're trying to retire old fossil fuel plants. That leaves this huge gap for what we call baseload power. That's the stuff that has to be on no matter what, 24/7. It's a real dilemma. Now, for a long time, nuclear power has been one of the main answers for that baseload problem. But the next-gen reactors we're talking about today, well, they aren't just a simple upgrade. We're talking about a fundamentally different way of thinking about nuclear. So what exactly makes them so different? All right, this is where you can see the huge technological leap. For, 60 years, the standard has been light water reactors, or LWRs. And like the name says, they use water at really high pressure as a coolant. These new advanced designs, they ditch the water completely. Instead, they use coolants like liquid sodium or molten salt. Now, that might sound like a small change, but the impact is massive. It means they can operate at low pressure, which is a huge safety win, and, get this, they can squeeze way, way more energy out of the exact same amount of fuel. And here's a number that just completely changes the game. According to the IAEA, these fast spectrum reactors can boost the energy they get from uranium by 60 to 70 times. Let me say that again, 60 to 70 times. To put that in perspective, that's kind of like taking a single log for a fireplace and getting enough heat out of it to warm your house for decades. It's an absolutely incredible leap in efficiency, and it's what could make our nuclear fuel last for literally thousands of years. So how is that even possible? Well, it all comes down to a concept called the fast reactor. And what's really fascinating is that according to the sources, this isn't some brand new idea. Nope, it's actually been kicking around for a very, very long time. So what exactly makes a fast reactor fast? Well, here's a simple way to think about it. Traditional reactors use something called a moderator. It's usually just water, and it acts like brakes on the neutrons, slowing them way down. Fast reactors, they just take the brakes off completely. This lets them use the most common type of uranium out there, U-238, which makes up more than 99% of all natural uranium, but is basically useless in traditional reactors. It's a bit like suddenly discovering how to run your car on sand instead of gasoline. It just unlocks this massive untapped fuel source. And check this out. This chart is from way back in 1969, but it's amazingly ahead of its time. See those top lines shooting way up? That's how much new uranium mining we'd need if we stick with conventional reactors. It's a ton. But now, look at the lower curves for these breeder reactors. The demand almost flatlines. They basically stop needing new fuel. And that's what could transform nuclear into a genuinely sustainable power source for the super long term. And this timeline really drives that point home. This isn't some brand new, untested idea. The basic science was proven to work way back in the 50s and 60s. So why now? Well, it seems to be this perfect storm of two things. First, the urgent need to deal with climate change, which the IAEA highlighted back in '09, and second, this crazy energy demand we're seeing right now in the 2020s. Those two things together have finally created the right moment for private companies to dust off those old blueprints and actually start building. I mean, just look at this diagram. This is from the 1960s. It's a full-on blueprint from Oak Ridge National Lab for a molten salt breeder reactor. The fundamental ideas that companies are building right now were already drawn up and detailed more than 50 years ago. It's pretty incredible.
Okay, so to make all this a bit more real, let's zoom in on one of the big players actually doing this stuff, TerraPower. They're one of the companies at the forefront of turning this decades-old theory into a real-world working power plant. So, TerraPower, you've probably heard of them. They were founded by Bill Gates back in 2006 with a huge goal: use this tech to fight climate change. Their main project is called the Natrium reactor, and it is definitely not just a theory anymore. As you can see right here, they are literally breaking ground on a demo plant in Wyoming. This is a huge step from the drawing board to the real world.
Okay, so how does this thing actually work? The Natrium design is pretty clever because it's not just a reactor, it's also a massive battery. Here's the gist. The fast reactor core gets incredibly hot. Then liquid sodium, which is amazing at moving heat, transfers all that heat over to a huge tank full of molten salt. That salt tank basically acts like a giant thermal battery, storing up all that heat. Then, whenever the grid needs power, they just use that stored heat to make steam and spin a turbine. This means it can dial its power up or down, which is perfect for backing up solar and wind. And all that high-temperature heat leads to another huge win: efficiency. We're talking about projected efficiencies of around 44%. Now, that might not sound like a lot, but traditional plants are closer to 33%. That is a massive jump. Put simply, it means you get way more electricity for the same amount of heat you generate. And that efficiency, at the end of the day, is what could make these new reactors actually affordable and competitive. But here's the thing: TerraPower is not alone in this. Not by a long shot. What we're actually seeing is this whole new ecosystem of innovators popping up, all competing. It's almost like a new nuclear race is kicking off. And this is where it gets really interesting. It's not just one horse in this race. You've got all these different approaches. So while TerraPower is betting on liquid sodium, you've got a company like Nucleo using liquid lead. And then there are others like X-Energy working on something called pebble bed reactors, which use these tiny, super tough little fuel pellets. It's this variety, this competition of different ideas that really pushes the technology forward and makes it more likely that one of them is going to be a true game changer. So what's driving all this? Well, it's not just government money anymore. The real rocket fuel here is market demand. I mean, when you see tech giants like Meta and Amazon, companies that need an almost unimaginable amount of clean, 24/7 power for their data centers, when they start investing directly, you know something big is happening. The market is basically screaming that it needs this technology, and it needs it now. So it all comes down to this one big question. After spending decades pretty much on the shelf, the technology to power our world cleanly, for centuries, is finally stepping into the spotlight. Now, the road from the lab to the actual power grid is going to be tough, for sure. There are huge challenges, but the potential payoff is just immense. The next decade is really going to be the test. We're about to find out if this old idea, brought back to life, can truly become the cornerstone of our clean energy future.